deals with two functions that you know a lot about, but eventually want to get to their derivatives, of course. That's the whole purpose. So we're going to talk about the exponential and log functions. Why do you think they are in the same chapter? Why these two functions are in the same chapter? What do you think? What do we know about these two functions before we go into detail? Why would they be in the same chapter? Is there something special?
They're inverses.
Brilliant, thank you, Sammy. Yes, they are inverses of each other. So for example, x over 2 is the inverse of 2x. How do I know? Because if to x over 2, I plug in x over 2 in x, I get x. If I plug 2x in x, I get x. So this is a pair of two inverses functions, inverses of each other. Here's another. Let's say, although there are some restrictions on this example that I was going to give, the square root of x and x squared. This happens for every x. This doesn't happen for every x, but they are inverses of each other. If I square this, I get x. If I take the square root of this, I get x. So that's the idea with inverse functions, right? We know the function composition of f with the inverse, or vice versa, will always equal x. In other words, if I apply this function to x and then this one, I get x. If I apply this one and then this one, I get x. If I apply this one first and then this one, I get x, and so on and so forth. So that's why the exponential and log are in the same chapter, because they are also inverses of each other. Okay, now let's refresh our memory on exponentials. Can anyone, it's okay if you're wrong. Exponential functions. Can anyone give us an example of an exponential function? I will write it here. F of x. Any exponential function that you can think of. Why is it called exponential? If you understand the name, then you will come up with an example.
X squared minus 5.
Careful. X squared minus 5 is quadratic.
Would x to the negative fifth power be exponential?
Say it again.
X to the negative fifth power.
This is 1 over x to the fifth is rational.
Damn.
That's okay. Let me explain. If it says exponential, the power is the variable. So, go ahead.
I was gonna say, would it be 2 to the x?
Exactly. Power? That's it. That's why the name. Exponential. See, I exponent. So I'm sorry, I swallowed an N here. Exponential. So it's called exponential because that's where the variable is. It's the exponent. This is called the base. So there are two shapes. Two shapes. One with a base that is greater than 1, and a different one with a base less than 1. But let's analyze one thing before we continue. Can anyone give us the answer for 0 to the 5th?
Would it used to be 0?
Excellent. Can anyone give us negative 1 to the 3rd?
Negative 1.
Excellent. Can anyone give us 1 to the 5th?
1.
Excellent.
1.
Perfect. One more. Negative 3 squared.
9.
Excellent. However, these are not allowed in an exponential function. What is not allowed? What am I saying here? The base cannot be 0. The base cannot be negative. And the base cannot be 1. So this number, which is the base, cannot be 0, cannot be a negative number, and it cannot be 1. And you can say, what's the big deal? You have the answers. They all exist. Yes. But if we allow these bases in the exponential function, its inverse will not exist. So we cannot allow the exponential function to have base negative, 0, or 1, because this will not exist. So what can the base be then? So let's clarify it. So I have to look in both videos. Okay, so the base can be, it's denoted by A or B, it doesn't matter, has to be either strictly greater than 1 or a tiny number between 0 and 1. As you see, 0 is nowhere to be found. It's not here. As you see, 1 is nowhere to be found. That was my calculator on the floor. And it cannot be 1. And you see, it cannot be a negative number. It's either positive to the right of 1, bigger than 1, or small positive between 0 and 1. Therefore, the two shapes. So we're going to look at f of x equals 2 to the x. And we're going to look at f of x, a number between 0 and 1, let's say 1/3 to the x. They look differently. The shapes will be different. So, if you remember from your past experience with these functions, the one that has a base greater than 1 is what we've been confronted with for the last 4 years. It was an awful situation. 10 people got sick here. 3 days later, there were 10,000. 4 more days, or 1 million. It was 1 million. This was the pandemic. It was horrible. That's why they said we want to flatten the curve. We want to flatten the curve and eventually come down to 0 possibly. But it was going like that. Insane. The number of people was getting sick was increasing tremendously. Dangerous. So please remember, this is a function like 2 to the x, 10 to the x, e to the x, any base that is greater than 1. They all have the same shape, growing up, increasing all the time. This one has this shape. Same with this one, but always decreasing. As you see, this is always decreasing, and here the base is between 0 and 1. What will they be? Examples: 1/2 to x, 1/16 to x, and so on and so forth. And here, so on and so forth. Now, these two are super important, and they have special names. This one is called common exponential function. This one is called natural exponential function. Okay, so I'm picking up my calculator from the floor. Okay, here it is. So important. These are so important that you see they have special keys. Here, right here. 10 to the x, e to the x. We activate them with the second key. Second, 10 to the x, second, e to the x. Super important. Also, notice one thing. They share the same key with log. This one shares the same key with ln. There must be something about it, and we're gonna get to that. So now, I hope you remember that when we graph, if we have to graph, the function and its inverse, first I have to graph y equals x. Y equals x is the simplest possible linear function, and what it does, it bisects these quadrants. It divides them in half. This and this are the same, this and this are the same. Of course, these are identical. So what am I trying to do now? I'm trying to graph. I graph the function with base greater than 1, exponential. I graph the function with base less than 1, exponential function. Now I want to show how to graph their inverses. So what will the inverses be? So the inverses must be symmetric, the graphs. Symmetric. WRT with respect to y equals x. So when I graph them, they better be symmetric with respect to that line, the orange line, y equals x. And must have the exact base. If this one is 2 to the x, the log has to have base 2. If this one is 10 to the x, the base of the log has to be 10. If this one is e to the x, the base of the log has to be e. Same thing here. If this one has base 1/2, the inverse function has to have log in base 1/2. If this is the shape of 1/16 to the x, the log function must have the same base. And the graph has to be symmetric with respect to y equals x. Okay, so I'm going to graph symmetric graphs. If this one is increasing, the log will increase. And I have to graph a mirror image of this graph with respect to y equals x. This is its inverse of that. Notice that this one does not cross y equals x, but this one does. The other one, the inverse function, must cross at the same point. Not here, not here, not here. Exactly at the same point. If it doesn't, that's fine. So notice again, and we're going to name those in a minute, but notice again this. I'm folding with respect to y equals x. My graphs are not perfect, but the two graphs, the green and the black, have to overlap. Same thing here. If I fold the graph with respect to y equals x, the two graphs have to overlap. Okay? Good. So now let's name these functions. We haven't named them yet. So, if we're looking at 2 to the x, the inverse function is log base 2 of x. In case you don't remember, I'm going to write the way we read it right here. Log base 2 of x. Log base 2 of x. These two functions are inverses of each other. If the base is 10, that's my page 3. So if we have base 10, which is the common exponential function, the inverse function is log x. And you can say, what happened to the base? Well, it's there, but we don't write it. 10 to the x and log are inverses of each other. So if this is common exponential function, of course, this is common log function. And one more. If we have e to the x, which we know is the natural exponential function, the inverse function is denoted by ln x. And you can say, why ln if it's natural log? It comes from German. So that's why it's ln and not nl. Not natural log, but natural log. Okay? So this is the natural log function. You can say, but where is the base? It's there, but we don't write it. So when we talk about ln, natural log x, you have to remember it has base e. When we talk about log x, you have to remember that it's base 10. Okay, and one more, let's say 1/2 to the x power. Can anyone give us the inverse function of this? It's okay if you're wrong. What do you think? This-
Log base 1/2.
That's it. That's it. Log base 1/2 of x. That's it. Awesome. Who was that?
Samantha.
Thank you. Good. Now, there is a very, very important relationship between log equations and exponential equations. Very important relationship. So here is something called double equivalency. What does it mean? What I'm going to write here implies what I'm going to write here. And what I'm going to write here implies what I'm going to write here. So from here I can get this, and from here I can get this. Log base a of x equals a number y. This is a logarithmic equation. And here's how we write the equivalency. So the log equation is equivalent to an exponential is equivalent to a log. And we start from the base, always, counterclockwise. From the base, counterclockwise. A raised to y equals x. This is the most important relationship. Without this, we cannot solve equations. We have hard time with all sorts. So any log equation can be converted into an exponential. Any exponential can be converted into a log.